Okay, today we're going to be talking about unsupervised learning and generative models in particular. We, stepping back, have in this class finished our modules on supervised learning. We've looked at CNNs, RNNs. We've done an entire module on reinforcement learning, and now we're picking up unsupervised learning. This is the last module, and after this, we will end. All right, so let's get started. The goal for today is we'll look at unsupervised learning, and the overall goal for this module is we'll get at a few generative models, pixel RNNs and pixel CNNs today, and variational autoencoders over the next couple of lectures, finally culminating in generative adversarial networks, or GANs, which you may have heard a lot about. All right. So let's take a step back and compare what we've been doing in this class and compare and contrast supervised reinforcement and unsupervised learning. So everything that we've done in this class started out with me in lecture 1 or lecture 2 telling you that all of supervised learning, I'll reduce it in a slide to a single slide where it was a mapping from X to Y. X was input, Y was output. X is the data typically, Y is the label. We've sort of related this to classification, regression, object detection, and in this X to Y mapping, the role our neural networks were playing is that X was input, Y was output. Neural networks were differentiable computational engines, and we were going to learn those parameters by minimizing some supervised loss function like cross entropy or L2 loss function. And we basically turned that crank for other tasks as well, semantic segmentation, where this per pixel annotation was Y, but it doesn't really change this sort of an architecture where you sort of deal with, we had to come up with new architectures to do pixel-to-pixel semantic segmentation. We had to teach you CNNs, we had to teach you deconvolution or transpose convolution layers. We had to define pixel-level loss functions, but everything else stayed the same. In order to do, for example, image captioning, where input was image X, it is this, where the image was X, the output was Y, but this game of going from X to Y didn't change. In order to generate Y, we had to teach you recurrent neural networks, but we were still learning a functional map from X to Y for these tasks. In reinforcement learning, that changed a bit. We no longer had an clean input-output X-Y mapping, but we sort of came up with a few different ones on our own. We defined, first of all, the learning paradigm change. It was not a supervised learning paradigm, meaning that we did not have explicit labels. We just had an evaluative feedback in terms of a reward. But what we ended up doing is that, for policies pi, we ended up learning a mapping from ST to AT. So sure, X to Y changed, but as far as deep policy learning, it sort of changed stayed exactly the same. We learned a mapping from states to actions. For Q learning methods, sure, it was a mapping from ST, AT to a real valued value of how good this action was going to be, or it was from ST to a vector values for each of the actions. And if we learned a model-based function, we would have just learned probability of ST given ST plus 1 given ST and AT, and this would have been, we would have modeled this with a neural network. So it's taking in a triplet and outputting a scalar. That would have been our neural network. We played around with different architectures, but it was essentially a similar game from input-output mapping. Unsupervised learning is going to be fundamentally different, but it's going to continue this loop or this arc of reduction in supervision. In unsupervised learning, there is just data, if you will. There is just an input X, and there are no labels. There's sort of no expected outcome. And our goal is very different. There is just the goal at a high level is to learn some underlying hidden structure of the data. Notice that that is a sort of imprecisely phrased statement. It is not a formal statement. What does underlying hidden structure mean? And what does learning an underlying hidden structure mean? How do you know you're doing well? How do you know you're doing poorly? What is the objective function? All of these things are a lot easier in supervised learning because you know that there is some user specified function like accuracy. You know when you're doing well, and then you may not optimize accuracy. You may optimize approximation to accuracy like cross entropy, but at least you know how well you're doing in terms of that objective. One of the fundamental difficulties in unsupervised learning is that it is a imprecisely specified goal. We can specify it at an abstract level, but we have many different instantiations of what it means to learn some hidden structure of the data. For example, if you're doing clustering, learning a hidden structure of the data just means creating groupings of the data. Under some metric function, you come up with some way of measuring distances or similarity, and you come up with an algorithm that will give you groupings of data points under this similarity function or this distance function. That is telling you some hidden structure, which is a clumping or a clustering of your data. And then you can come up with an objective function that measures that. There are other methods which are dimensionality reduction. Your data lives in some high dimensional space, let's say some 3-dimensional space. What you want to do is you want to learn about axes of variation in this 3-dimensional space. You want to know some axes that have large amounts of variation, some axes that have small amounts of variation, and you want to use it to project your data from 3-dimensional space to a 2-dimensional space. And that is telling you some structure in your data, because this data is not really living in 3 dimensions. It is actually just living in 2 dimensions because there isn't variation in the 3rd dimension. And this is one definition of underlying hidden structure. And under this definition, you can define objective functions and know how well you're doing. There is, of course, density estimation as well, meaning that what we want is to learn a probabilistic model, P of X. Which means that given X, we want to, give you a number P of X. If X is discrete, then P of X lives on the simplex. If X is continuous, then it's a density function. And I want this density function because I want to know whether the data I'm looking at, is that rare? Is that frequent? Is the event I'm looking at an outlier, or is this exactly what I should have expected? Given the time that we're in right now, polling and expectations are particularly on our minds, right? Like, are we looking at outlier events, or are we looking at things that we should have expected? And that's the job of density estimation. And density estimators also tell you, allow you to make conditional queries, so that if X is a vector that consists of some subcomponents x1 through xd, then density estimators allow you to ask what happens to xi as I tell you xj or j plus n or something, some list of variables. I can make conditional queries. And this is one definition of underlying structure, which means how is the data distributed in this space. And with this objective function, you can come up with log likelihoods and probabilistic interpretations of the objective. So those are a few different meanings of this imprecisely stated phrase of learning the underlying hidden structure. One of the reasons why we have this phrase underspecified is because the goal of unsupervised learning is often for some human consumption or something downstream, where you want to learn something about your data. It's a process of discovery, and processes of discovery are often underspecified by their very nature because we do not know what we're looking for. If we knew, then it wouldn't be called the process of discovery. So it's important to keep in mind. One thing I want to mention is that there is a clear sort of analogy between supervised and unsupervised learning. So if you start with an input X and you're going to output Y, and the Y is discrete, in supervised learning, that would fall under classification. If Y is continuous, that would fall under regression. In unsupervised learning, if you're mapping X to some C and that C is discrete, then this would typically fall in clustering. If it is, this exact symbol doesn't matter, but if we're using Z and that Z is continuous, this is typically what would fall under dimensionality reduction, particularly if Z is lower dimension than X. If we're mapping to a density function or a mass function, so this is simplex if X discrete, otherwise it's a density function, then this would fall under density estimation. So there's a taxonomy of these tasks. It is important to sort of put these side by side because you can directly compare what we are looking at. In supervised learning, there is someone formulating the problem, which is typically, as machine learning experts, you are going to be formulating this problem, where you decide that there is this variable Y, which is your prediction variable that you're interested in, and you typically go to annotators to get them annotated. In unsupervised learning, there is no such prediction variable. This is both a strength and a weakness. Training data, or just data without annotations, is typically cheap. It is not expensive to just get data. In computer vision, for example, getting access to images is not that difficult because there are already existing repositories of images online. If you're dealing with autonomous driving, getting access to LiDAR point clouds is not that expensive. You can just sort of stick it on a robot or a car and have it drive around, and you'll capture these. Anything that can be sensed directly through sensors is typically not expensive. It may not be trivial to get, but it's not as expensive as annotation, which is where are the people in these images? Where are the street signs? Where is this a disease outbreak or not? It is expert domain knowledge that is typically captured in the annotation of Y that tends to be expensive. X tends to not be that expensive. And so in that sense, a holy grail of unsupervised learning is to learn directly from just observing data, from your sensory observations. And so in that sense, this is a sort of rich, open learning problem. Yes, it is underspecified. That means plenty of work here to be done. So if this area of research has gone through certain renamings, this is sometimes studied under unsupervised learning. In the last few years, this has been called self-supervised learning. This is what we had the guest lecture on. Self-supervision essentially just means that generating Y from parts of X, where Y is a pretext task. And so we've looked at an entire lecture on that. Mixing data sets where some have Y, others don't, falls under the domain of weakly supervised learning or semi-supervised learning. Okay. So let's take a quick dive into k-means clustering, a vanilla algorithm that forms the building block for understanding a lot of other more sophisticated algorithms that we'll get to. This first part will have nothing to do with deep learning. You may already have seen k-means clustering in a machine learning class, an intro to machine learning class, but just in case people haven't, I think it's important to establish this understand this as a simplest abstraction of unsupervised learning before we can move on to more sophisticated things like Gaussian mixture models, and then ultimately VAEs, which is what we're building towards. Okay, so here's what k-means clustering looks like. You are given a data set. Every point here is a point in some d-dimensional space. We do not know. This is a two-dimensional. This is a two-dimensional visualization, but the data may live in some arbitrary high-dimensional space. Okay, so back to k-means, we have a data set of these points. They live in some high-dimensional space. Each one of these is just some xi. K-means is a fairly simple, it's an elementary algorithm that we have to understand as a building block. It asks a user how many clusters or groupings of the data would you like, some positive integer, where a user specified parameter k, and that's why it's called k-means. Let's say the user specifies 5. The algorithm randomly initializes. If xi lives in RD, so x is each data point. If x lives in RD, mu j is the jth cluster that also will live in RD. We're going to initialize, 5 of them randomly in this space. We are going to assign each data point to the center that it's closest to. This is in computational geometry known as Voronoi cells. But if we have picked a cluster center, for each data point, these lines are indicating that every data point within these cells has this particular cluster center as its closest cluster center, meaning that I pick any xi, I find distances to all all cluster centers, and I assign it to the closest under some distance metric. Once that's done, after I have this assignment, each center finds the centroid. Each cluster finds the centroid of the points it owns, meaning that given that I now know that these are the points that fall in this cluster center J, I can re-estimate the mean and I can move this around. And that's it. I just sort of repeat this process till convergence, if you will. And there is actual convergence in k-means in a very specific sense. And you can prove this if you write down the objective as well. So if you change these distances to some d, it won't be a centroid problem. It will be medoid or some other, some sort of minimization of an objective, which is a function of the distance. Let's take a look at a quick demo, because I personally find these things to make sense, visually a lot easier to understand. Here is a particular. I do not like this distribution at all. Much better. Okay, so this is a really nice demo illustrating k-means, and I'll tell you why I didn't like those points in a couple of seconds. This is a distribution of points. Notice that they already look kind of Gaussian. They look clumpy. It's because L2 distance in k-means can be, with L2 distance, k-means can be considered a approximation to Gaussian mixture modeling. And so if you know about Gaussian mixture modeling, then this may be clearer. This is why all sort of demos of k-means tend to have these sort of data sets. But this is our data set. We have 3 of these cluster centers that have been spawned, the orange, the red, and the green. We can find the closest cluster center. So here are all the points that have been labeled in blue. Here are points that have been labeled in orange. Here are points that have been labeled in green. We can now update the centroid. So the points moved. We can find the closest centroid again. And we can keep doing this over and over again. And at this point, we appear to have convergence. Convergence in the sense that the assignment of data points to cluster centers is not changing. That is a discrete object. And if that object is not changing, meaning that if you have the same data points assigned to the same cluster centers, the cluster centers won't change either. So this is a assignment, or this is a convergence of one run of k-means. K-means is not optimizing. So first of all, k-means is optimizing an objective. We can write that down in one slide. K-means is not it does not find the global optimum of that objective, and it is dependent on initialization. So if we actually initialize cluster centers again and repeat, we may find a different assignment, and we may find something that is a better objective of k-means. So now we have put this blue cluster center exactly on this clump, green here, orange here, and we did not see this in the previous round. We did have convergence, just not to the global optimum of the objective. There's a new centroid, we can repeat, and we may find a third result, which is different. You can often, in these cases, by the way, notice that this is a two-dimensional data. We're looking at the data, so we can very easily say that there must be 3 cluster centers. In most of these cases, you may pick a number that is higher than the true number of clusters, and so you can end up with something where your underlying clusters are found, but certain things are found that are not really representative. They're just noise, if you will. You can also have cases where you guess a number less than the true cluster centers, and then you can see that you may discover one cluster, but really the cluster center in this case, because you've initialized with 2, is not representative. The center does not actually give you any indication of density around that point. So this point actually has the fewest number of data points around it, but it's because we have under-segmented this cluster. Okay. All right. So with that demo out of the way, we can actually give a fairly formal interpretation of what k-means is doing. We can define an objective function, and that objective function measures distortion. This objective function f can be in terms of mu, the cluster centers, and c, the cluster assignment. So what we can do is we can enumerate over all data points. We can find the distance of xi to the cluster center that it's assigned to. So notice ci tells us what ci is a value in 1 through k. It tells us what cluster ID the ith data point is assigned to. And so this expression is telling us the distance of xi from mu j if ci is equal to j, right? And so this is telling us the distance of xi from the closest cluster center, and we're summing this over all data points. And this is in an objective function. We can also convert ci into a 1 of k encoding. So I can write down ai as a vector, and I can say that this is, this consists of ai1, ai2, all the way till aik. And I can say aij is 1 if and only if ci is equal to j. So aij is 1 if the ith data point is assigned to the jth cluster, which means I put a 1 somewhere and I put zeros everywhere else. And then I've just basically written that same objective in terms of aijs. These are indicator values, and these are the distances. With this formulation, k-means is basically coordinate descent. It's minimizing over mu, minimizing over a's, and it's just alternating between those two steps. And so this is the formal objective. This is a sum of distortion objective, and I call it distortion because you can relate this to compression. You can say that if I replaced xi by the closest distance, by a one sort of prototype or a data cluster center, and then I recovered it at the other end by just replacing xi by mu j, how much compression artifacts would I suffer through? What is the distortion? And so this is that reconstruction objective, if you will. So we have now understood, k-means is basically coordinate descent. Fix A, which means fix the cluster center assignment, and minimize mu. This is the cluster center estimation step, and the other step is fix mu, minimize over A. When you fix mu and minimize over A, this is the reassignment step, and when you fix A and minimize over mu, that's the cluster center estimation step. And if with the L2 loss functions, minimizing is the same as finding the centroid, but this is not always the case if your distance is not L2. So I'll leave it at there. This at least gives you a sense of an algorithm. We understand its objective function, and I wanted you to really understand the objective function about what we're doing. But that's sort of where we'll leave it. So here's a second, really a fundamental class of unsupervised learning techniques, which is density estimation. Here. Apologies. Here, you are given X, and what we want to do is we want to fit a density function. So we want to know P of X. This can be a parametric or a non-parametric model. We will talk about those in a second. But our goal is that, if we can fit a P of X function, then we can use it to answer queries. And I would claim you've already met a density estimator before, and I'll make that connection in a couple of seconds. So generative models are a fundamental class of models that are used to tackle density estimation problems. So generative models have this objective or this goal, this high-level goal. I haven't given you an objective function yet on the slide, which is I come to you with some data. This is my data set D of x1 to xn. This is a data from some data generating distribution, P of data. We do not have access to P of data. We just have some samples from it. And what I want you to do, so this is input. I like formulating things as input and output. And so on the left is input, and on the right is our output. What I want you to do is to generate samples, X, from this P of model. I want you to generate new data that looks like the data that I have I have access to. And one way of doing this is I want you to learn a P of model similar to P of data. So I want you to learn the underlying distribution that I have this data from. To generative models, this is our goal. We have some input. There are some example images or some text. They come from underlying distribution. We want to generate more of that type. This is one problem. You can, this can be achieved by wanting to learn P models similar to P data. That's the density estimation part of it. This is density estimation right here. And notice that I want to relate the word generative to something that you may already have seen before. You may have heard of things called generative classification versus discriminative classification. And in the context of classification, generative classification typically refers to this idea that instead of learning P of Y given X, what we will learn is P of X given Y. X is input, Y is output. We will learn what images look like that contain cars. We will learn prior over cars, and then we will use Bayes' rule to get P of Y given X between these two terms. We'll say P of Y given X is P of X given Y times P of Y divided by marginal of P of X. And this approach is called generative classification because this part is a generative model of X conditioned on Y. Discriminative classification is directly learning P of Y given X, which is what we've been doing in this entire semester. We've directly been fitting neural networks that go from X to Y. Density estimation is just about, or generative models for density estimation are just about P of X. This, by the way, can also be a generative model. This is a conditional generative model that generates P of X conditioned on Y, but we will not study these today. We will just focus on P of X. Okay. So why would you, there are a couple of different flavors of generative models or density estimation. Explicit density estimation explicitly defines and solves for a P model. So if you first, as an intermediate step, learn a P model and then sample from it, that would be explicit density estimation. Implicit density estimation does not actually give you a P model. You just have a mechanism. So X generated from P model, I can treat this as a black box So I have a process that creates this sample X without you having access to the P model, or anyone, or even my model having an explicit P model. That would be an implicit density estimate. Why would you want to do generative modeling at all? So first of all, there is a rich set of applications in creativity and art, but also in super resolution and colorization, where if X are images, P of X are fairly useful objects. But the same techniques that let you do P of X also let you do P of X given Y. They also let you do P of X given X prime, where X prime can be something like this. So X prime can be someone draws a particular sketch, and X is an image that your model learns to generate. So these are sort of conditional models, if you will. In this class today, we'll study P of X directly, but everything that we teach you will be directly applicable to these sorts of models. Generative models of time series data can be used for simulation and planning in reinforcement learning. These are sort of models for trajectory p tau, so state action trajectories can be considered generative models. And we will also tell you how they can be used for feature learning. Okay. There is a broad taxonomy of generative models. There are sort of what I already mentioned. There is a key distinction between explicit and implicit density models. Implicit density models, the main member of that family that you probably have already heard of are GANs, generative adversarial models, generative adversarial networks. Generative adversarial networks are implicit density models, meaning that they do not have an explicit P model. They do not have a probabilistic interpretation. You cannot give GANs an image and ask for the probability assigned to that image. That cannot be done. But GANs can give you X, which is sampled from some implicit P model, and they can generate new samples for you. They just have this process down as a black box. And this is because they're implicit density models. Explicit density models also give you access to a P model of X. They give you this artifact or this API back so that you can then bring your own data set and you can compute log likelihoods over your data set. And this is one of the reasons why evaluations of GANs is so challenging, because we cannot compute log likelihoods of data sets. Within explicit density models, there are two subfamilies. One where we make assumptions such that P model is a tractable function. Tractable meaning that we can explicitly and easily compute it in, let's say, some polynomial time or some low complexity. And then there are approximate density models where it is intractable. They require integrals to be solved for P model to be computed. And we do not have exact algorithms for computing P model of X. We have approximate algorithms, and that is where variational autoencoders fall, among other things as well. So this is a nice sort of mental hierarchy of concepts that you should be aware of. Today, what we will do is we will tell you two of these methods, pixel CNNs and pixel RNNs, and VAEs are things that we're building towards, and GANs is where we'll get to, but it's good to sort of keep this mental map in mind. Okay. So let's take a look at, as I said, we'll discuss three of these most popular generative models. Let's take a look at pixel RNNs and pixel CNNs. Pixel RNNs are explicit density models, meaning that they are learning. This is our P model of X, meaning that there is some parameterization theta that we are learning. They use chain rule to break Px down into Pxi given some ordering of X. So X lives in some RD. There are some, x1 through xi and minus 1, some linear ordering that we've done of these variables. Each one of these terms of these chain rule, we are just going to use a neural network to fit in. So meaning that we're going to say x1 through xi minus 1, we will enter that into a neural network. It will have some parameters theta, and it will predict, x xi, or more specifically, p of xi given x1 through xi minus 1. And then our objective function or our loss will be log probabilities. So we know what xi gt is, what the right one is, and conditioned on that, we will minimize the negative loss over theta or maximize the log probability. And so this is going to be our objective function. And notice there was no y used here. There was just parts of x to predict other parts of x. And I claim that you have already met this sort of a density model before. Does anybody remember, if you want to say in chat, have in previous lectures, is this reminiscent of anything that you've already seen before? I've seen this exact thing before in RNNs, where we X were tokens or words in a language. You had a data set of multiple words, and we converted this into a sequence modeling problem. But fundamentally, this is a more general idea than just sequences of tokens. This can be applied to arbitrary input X by just coming up with the sequence yourself. So even if pixels in an image don't have a natural sequence, you can convert them into a sequence. Right. So we will need to define an ordering of previous pixels, and we can do that. So you've met this concept in character level language modeling, where there was a natural ordering to the characters, and we did p of xi given w, log maximizing log probability xt given 1 through t minus 1. For pixels, we can define an ordering, which can be a raster scan ordering. So maybe we go one row at a time, meaning that, and one way of doing that is to define dependency, that each pixel affects its neighbors to the right and left. And so this, I can define a two-dimensional RNN which by the way, is similar to the multi-layer RNNs that we had shown, that if this is x of r comma c, then it depends on x of r minus 1 comma c and x of r comma c minus 1, right? So this is an RNN that concatenates those two previous variables into its input and converts hidden encoding, right? So I can define H, which is the hidden representation in an RNN or an LSTM, by concatenating these two pixel values. And this gives me a linear ordering. So I can go in raster scan order, and at any when I reach a pixel, I have obviously observed the pixel to its left and top. And I can, from those two and the hidden representation so far, try to predict the pixel value at this pixel. So I've converted just a data set of images into an RNN type conditional explicit density modeling problem. And at test time, I can do the same thing. I can sample, I can argmax. Everything that we taught you in sampling was linear left to right. The fact that there is a two-dimensional ordering here just means that you now have to keep track of this diagonal forefront, but you can still sample. You first sample x of 0, 0, then you sample these values and so on. And you can sample them based on the pixels that came before them. Since we are estimating each pixel at a time, isn't this computationally slow? Yes, excellent question. Right here. Yes, this is very slow. This sequential generation, the generation is slow, and even the training is slow, because the training requires, at training time, you have to do probability of xr comma c conditioned on the pixels that came before it in that ordering. And in order to compute the loss, you have to operate in a sequential manner till you have computed h, or the hidden values of those of the variables that came before it. You cannot compute this. So yes, this is very slow, and we will give you other techniques that are faster at doing that. Okay, and in fact, one technique that immediately came a year after pixel RNNs was pixel CNNs, which solves the problem of slow training time, but still doesn't solve the problem of slow generation time. And this is a different architecture that says Well, I can always do, I can still generate image pixels starting from the corner, but what I can do is I can limit the dependency using a CNN over a context region. So here is my window, and what I can do is based on these pixels, I can try to predict this particular pixel whose value I'm discretized between 0 to 255. I can try to predict based on these pixels so far. So just on a small context, as opposed to RNNs that can model infinite context, I can just have a narrow spatial context, and then those parameters can be shared at all pixels. So this is a convolution operation. Notice that this pixel I'm showing is at the center. It can also be at the corner. That exact setting of that pixel doesn't really matter. What matters is that you're going to have to be careful because notice this is X, and the value we're predicting, so this is X, the entire image, and the thing that we're predicting is a particular pixel of this X, R, comma, C. Notice we obviously have access to that pixel, so we somehow must be careful not to condition on the variable that we want to be predicting, right, by using it in the convolution. And so, by the way, this can be done in a deep convolutional manner as well. So you can have multiple layers of convolutions predicting features at a particular pixel, which then ultimately predict the softmax value, which is over 1 to 255. We just have to be careful to do these things called masked convolutions, meaning that if we want to compute features or predict the value of X, R, comma, C, we have to be careful not to use that pixel to predict that pixel, because then you'll be conditioning all itself. You cannot generate that way, and you'll get zero. You'll get it. The neural network will learn identity, and you won't be able to go anything. And also, these zeros are basically enforcing the raster scan order, that they're enforcing that you do not look at future pixels to generate the current pixels. So this is called masked convolutions. And with that, you're basically again training to maximize likelihood of training images. I just need images. I don't need any labels. I do P of xi given x1 through xi minus 1 with some linear ordering of I, right? This is my ith pixel. And I have done some linear ordering from 1 through I. I condition on those pixels in the past, and I can generate a softmax for the ith pixel. And I can train this. I can learn parameters, not just of this filter, but if there's an entire CNN in between, I can learn those parameters by minimizing this negative log probability or maximizing this log probability. Okay. Training in pixel RNNs, training in pixel CNNs is faster than pixel RNNs because you can parallelize the convolution. Because you don't have to operate sequentially from the top left to the bottom right at training time, but generation still has to proceed sequentially. You still have to generate by sliding this filter, and it has to be generated one pixel at a time. You cannot implement the generation convolution in parallel because you do not have access to the pixels that you haven't generated yet. And so the generation is still slow, but the training is significantly faster than pixel RNNs. This is what these kinds of generations look like. So on the left are 32 by 32 TFAR10 generations, and on the right are 32 by 32 image generations. Pixel RNNs and pixel CNNs for images are not the state of the art in generating images. They are, and they never really did scale up beyond small spatial images, 32, 64, 128, but really never, 1 megapixel, 20 megapixel images. That just never happened. GANs with transpose convolution and other sort of heuristics and tricks are generally what has led to much higher resolution image qualities. And what you find in pixel RNN and pixel CNN type models is that they generate things that sort of look blobby and kind of have the high level statistics of the data set. If, in ImageNet, there's one center blob, which is the object, they'll generate that. But you can never really recognize anything, and there's not sufficient detail or clarity in the images. Okay. Because these are generative models, you can obviously do conditional estimation, right? If I have P of X, I can obviously condition on parts of X. So I can ask for P of X I plus 1 through D given Px 1 through I, right? So I can occlude parts of this model, and I can ask this model to fill in these pixels, condition these pixels, because this is a generative model. And what we find is that we can not only get a single, because this is a probabilistic model, we can sample from it and not just get one. So this is one sample, this is another sample, and so on. So we have 6 different samples that we're showing. And what we find is that, in a lot of cases, the model is filling in detail, which is fairly plausible. The grass regions continue downwards into the occluded parts. The texture of this animal is maintained, and you get reasonable looking completions. Here is, for example, a clearly circular object. You and I would estimate that the object would continue, and the model has picked up on that fact. There are some cases where odd artifacts and things are appearing, but it's clear that there is some sense of the structure of the data. This is what I meant by structure of the data being preserved or learnt, if you will. And this, hopefully now you see why it is hard to convert that ambiguous term to learn something about the underlying structure of the data into a formal objective. How do you capture the fact that, look, this model has learned that shape boundaries continue? There's no sort of formal objective that captures that. Could you also talk about the merits and demerits of equivalent of pixel CNNs in other domains like speech generation or text generation? Do they perform better in other domains compared to images? Yes, absolutely. I was going to go to that in the next slide. There's a really nice piece of work out of DeepMind. Actually, this might be a good time. That is what was the plan on the next slide. So there's a really nice piece of work from DeepMind on wavenets, which is a pixel RNN type method, or in this case, less a pixel RNN because there aren't pixels here, but using ideas from there for speech generation. So here is, if you haven't seen, here's the blog from DeepMind on WaveNet. It's a generative model for raw audio. I would say it is less similar to pixel CNN than it is to just sort of classical RNNs, if you will, where they sort of generated waveforms with sampling frequencies of 1 millisecond. So you're seeing that this visualization I really like because it gives you a sense for hierarchies or scales in which structure exists in the data. If you sample a waveform at the rate of 1 millisecond, you realize that initially there is this level of structure, but then there are sort of repeated waveforms that are coming together to form sounds and speech patterns that have a structure that only emerges the 1 second level. And they used ideas from pixel RNNs and pixel CNN models to also capture long-range connections in some of these things. All right, so I won't be able to. Looks like I won't be able to run this for everybody, but I encourage you to check out this webpage. There are very interesting examples of parametric speech generator just concatenating parts of other speeches from your data set, and finally the outputs of WaveNet. And you'll notice that they are far more smooth and sort of cleaner in their transitions, if you will, and sound much more naturalistic. So I encourage you to check this out. With that, we are essentially done. We introduced pixel RNNs and pixel CNNs. The pros are that these models can explicitly compute likelihoods. You can bring your own data set of real images. You can split them into train and val, and on the train, you can optimize parameters, and on val, you can measure log probabilities. So this is an example of unsupervised problem where you can know how well you're doing under your log likelihood objective. However, the generation is very slow, and the quality of images never really did match the quality that GANs were able to produce. And so this line of work did not really take off into becoming sort of the mainstream line of work in image generation. We will get to VAEs and GANs next. I just want to stop here